Hi, I'm Jeff Rosenfeld. I'm editor of the Bulletin of the American Meteorological Society, and here to talk about the sciences and the annual meeting for the AMS. This is our annual meeting. This is Greg Tripoli, who is not only a new fellow of the AMS, but of course a professor of Atmospheric and Oceanic Sciences at the University of Wisconsin. And Greg, it's a pleasure to have you here. Congratulations on being
Thank you very much.
fellow. You're obviously someone who has been in the field for a while, and my understanding is that your biggest area of interest has been convective storms and severe weather, various kinds. Is that an accurate description, or would
I'd say, yeah. Well, it's been, I've had a number of interests over the years. I've worked in everything from oceanography to hurricanes to mesoscale weather and convective systems, and now I'm even dabbling in climate type stuff. So as a professor, you're not really obliged to focus on a particular area of a research institution's mission. And in a department like ours, you can become much more broader, and that's one of the reasons why I've spread out.
How did you evolve then? Where did you start in the field?
I actually started in high school. There's a picture of me on the front page of Weatherwise in 1966, back when I was 16 years old.
Wow.
We had a very unusual science program in the high school, and Dr. Witt, or Mr. Witt, was our mentor back then, and a number of us, like Frank Marks, who works with you, and Jim Hack, and I, and Jordan Alpert, a number of us actually came out of that high school program.
Wow. Now, where was this?
This was in New York.
New York.
And we actually wrote some of our first models back then. And people from New York University and people from Florida State University mentored us and kind of recruited us out of high school. And so I eventually went to Florida State.
Wow. Wow. Now, that's an amazing thing to start so young, yet a lot of people in the field do start young, as it turns out. But to have that direction and that help to get started, that's great. What kind of models were these?
Well, they were barotropic models back in those days. They taught us enough from the university, the graduate students that came by and mentored us a little bit from Florida State, NYU. They taught us enough to be dangerous. They taught us a little bit about vorticity and things, and then we read textbooks and we learned how you can invect the vorticity and recover the height field and all this. And so we wound up writing programs in Fortran on the computers, which were owned by the school district. And we had to learn programming all by ourselves. We learned it out of manuals. It was a number of years after I learned programming that I realized you didn't have to use I and J as the loop parameters in Fortran program, because we learned out of the textbook that way. Or it was a manual, not a textbook. But we figured it out and got these things working, and that's how I got started.
Wow. So now you still work with models, obviously, and at this point, they're way beyond what you were looking at when you were in high school. How has that affected the kind of work that you've been able to do?
Oh, it's affected a lot. And back in those early days, models were kind of hydrostatic, filtered, very reduced models of the atmosphere. They made a lot of assumptions, and they really couldn't represent the processes that were going on, except based on some very simplifying context. But now we can, with the very large computers, we can simulate very small-scale processes explicitly within the context of very large models. This is never. It's a whole different world from what it was before. If you go back about 20 years ago, we had climate models, right? And these are things that simulate climate over a long period of time. And the way that you created a climate model was you tried to simulate the evolution of the statistics of the problem, because we weren't going to predict if there was going to be a snowstorm in Madison in 100 years from now. We can't predict that. we can predict if there's going to be more frequent snowstorms or more intense snowstorms in Madison 100 years from now. So what it was about is it was about being able to simulate statistics over a long period of time. And those were very distinct from weather models, because weather models were deterministic predictions of the future, a day or two in the future, and you're trying to get the weather as close as you could to exactly what happened. But now, what's happened is we've created these very small scales in the models because we have more resolution and more grid points. We can solve for all scales. We get down to the point where they ran in Japan already. They've run the first numerical model with 400 meters global resolution. Can you imagine how many grid points that is? But more importantly, can you imagine all the processes that resolves? It's resolving things like gusts of wind around buildings. I mean, on a global scale, how many of these things are going on? But here's what's really interesting about this. The fields that are the finest fields that you can resolve are in no way predictable. Just like the climate in the future, we weren't going to be able to predict a snowstorm in Madison 100 or 200 years from now. We wanted to predict the statistics. Now, when we look at these fine-scale features resolved, that are now resolved, it's the same problem again. In other words, all atmospheric models are now becoming climate models with the same set of goals that climate models had, like being able to predict the statistics, being able to conserve the things that are conserved over time so that you can evolve the statistics properly. So models have really evolved into a different thing than they once were. And this is our problem with relating to the public, because the public still thinks we are trying to predict a snowstorm tomorrow, and which we are, but at the same time we're predicting gusts of wind within that snowstorm. At some scale, as you get smaller and smaller, the scales that we can resolve into a 24-hour forecast, the predictability becomes very, very small, the deterministic predictability. But we still understand something about the statistics on the finer scales, just like climate, if you're following me on this.
Well, it's interesting that when we talk about seamless prediction as, trying to marry the weather modeling with the climate modeling enterprise, right? Mm-hmm. And there are pitfalls moving in one way or the other, it seems. And I guess what I find interesting is that you have this experience with weather modeling, and over the years you've moved into, you're saying you're moving into some climate questions. In part, it seems like you're moving into a new area, but having to adapt different routines or ways of looking at the models on both the small scale and the large scale to make that transition. You can't just go from one to the other.
One thing I'm pointing out here is, yeah, I'm looking at climate, but that's kind of a separate question. What I'm pointing out is that all models are climate at some scale. When you get down to the fine scales, like the gusts of wind outside, you're going to get gusts of wind all day. What you're predicting on those fine scales is the climate of the gusts of wind.
Because it's a statistical thing.
How will that vary statistically?
Yeah.
When will the gusts get stronger? When will they get weaker? You see what I mean? So you're predicting the statistics of the flow, which is what we've always done with climate models. So in a sense, all of our models are becoming like climate models, where climate becomes defined at some scale within the model.
Now, most people talk about the progress the other way, though. The fact that you're resolving smaller and smaller scales, therefore it's a little more like weather modeling. In other words, you can run a deterministic model for these larger scale questions, the more computing power you get. But you're saying it also goes the other way.
It mainly goes the other way.
Mainly goes the other way.
And like I said, the goals of climate modeling have always been about the statistics and things like being able to conserve the total amount of momentum field, the energy fields, being able to conserve quantities in a global integral sense was always the motivation of the climate model. Weather models were just trying to get a particular structure to occur at a later time. But with climate models, there was a totally different way that you approached the model. What we've done is we've evolved the weather models to the point that we have so much statistical information from the smaller scales, and yet we still, in most disciplines and within the science, they still treat them as weather models deterministic. The mathematicians approach it as a deterministic forecast, and they really should not be doing this because it's not a deterministic forecast. It becomes more and more deterministic at some scale, but it's not deterministic inherent. Now, you know what I mean by that.
Yeah, but also wondering, like, what kind of new tools are coming in to help deal with that in your work?
One of the most important aspects of it is certainly, there's a couple things. One of them is how you approach modeling, and with an energetic conservation type approach. That's one thing. But the other thing is, what do you do with this information? How is the public going to accept it? Now, the way I look at it, and I think the correct way to look at it, is that all predictions are probabilistic. The deterministic predictions are those with high probability. And what we can do is, for any prediction we make, we can have the goal of being able to say how probable this prediction is of being right. Because of the errors involved in the way we start the models and the errors involved in the models themselves, the error growth is very high. And we have no real hope of predicting the very small scale features very long. I think here's one thing you got to realize. Look at weather prediction from the beginning. What have we done? We think we've gotten pretty good. If you look at the 80s and 90s, we're 85% on some things. But what are we 85% on? We're 85% on middle latitude or extratropical cyclones, getting those right. Extratropical cyclones have a life cycle of 3 to 6 days. 3 to 6 days is the period at which we have fairly good deterministic predictions. In other words, we can predict the extratropical cyclone throughout its life cycle. Really, one life cycle of an extratropical cyclone is what we can predict. That's all we've ever been able to predict. With these models, if you look at them in the summertime, they do much worse when you don't have extratropical cyclones. And they call this the summertime prediction problem. Well, what happens in the summer? In the summer, you have a lot of convective storms, convective mesoscale systems, convective individual storms. What is the life cycle of a convective storm?
Very short by comparison.
20 minutes for an individual convective storm. And then you get convective systems, and the life cycles are maybe up to 3-4 hours. And therefore, that defines, if we're resolving those storms explicitly in the models, that's what we can predict, maybe out to one life cycle. So if we have a cumulus cloud, the time we could predict, at best, if we had perfect data, would probably be about 20 minutes.
So you're now getting to modeling systems that are dealing with items that are predictable on 20-minute scale and items that are predictable
Exactly.
on 4-day scales, and mixing all that together into one.
So when you make a prediction, what really, the part of the prediction that has to be articulated to society is the fact that this is a probabilistic prediction. And maybe the prediction for 1 or 2 days from now has a 90% probability it's right. There's still 10% it's wrong. But we can understand exactly how probable that's right, how high that probability is. But if you get down to the finer scales of that prediction, like an individual thunderstorm with a gust of wind coming by 24 hours from now, the probability that that's right is much lower than the probability that if you just use climate and not even try to make a prediction at all. So there's never going to be any skill in the finest scales. We just have to realize it. But there's been many discussions at the AMS conference on what do we do about this changing paradigm? How are we going to deal with this? And my feeling on this, that I try to convey, is that we're in an era now where it's no longer feasible to articulate to the public these kind of probabilities explicitly. I think the models and the weather predictions should be articulated electronically to your cell phone. You know, I mean,
like through
your
device.
smartphones and things. The smartphones can absorb this information, and what the public should be able to do is ask continuous questions like, well, are we going to have warm or sunny, sunny or thunderstorms, or what are we going to have tomorrow? And they say, well, there's a 80% chance there will be thunderstorms. Well, I have a thunderstorm right where I am. And it says, well, in your area, it'll show you the kinds of probabilities if you ask those questions. And you can, you can't exhaust your smartphone. So you can ask as many questions as you want until you're satisfied you understand what is understood. On the other hand, we have infrastructures and economic structures that are highly dependent on this weather information.
On deterministic information sometimes.
Well, it's deterministic because they don't know how to handle
Yeah.
the probabilistic, which is where the real information is.
Right. And in fact, I'm going to ask you this question. I mean, you can tell the public, just keep asking your mobile phone question, but I don't think people are trained to ask the right questions necessarily either. I'm just wondering if this is a positive thing or a negative thing.
Well, it's a positive thing because we could always devolve it to what we have now.
True.
The new information is what we want to give the public as much as we can, but it may be some limit to what we can do. Now, I think one of the approaches that should be done is through this electronic transmission of the information, feed it directly to the infrastructure. So like the wind farms would have an idea of the probabilistic nature. And if you want to take a wind generator down at some time tomorrow, it may say, well, this is not a good time because this is when I'm going to get my best wind. If you just wait 24 hours, there's a good probability that there won't be any wind, and if you take me down at that point, you won't lose anything. So all the infrastructure can absorb the probabilistic information without ever having to have some human there understanding what it sees. It can absorb that information and make the correct decisions to make the efficiency best. So I think we're moving to a future where this information will be fed directly into the infrastructure. I learned this from the military years ago.
How is that?
The military has already, even back, we were working on weather systems for Afghanistan, after the 2001 attack. But one of the things they were already doing is taking these high resolution models and absorbing that information directly into their infrastructure of artillery and things like this. And when they were in these fields of complex flow in mountainous regions where flow is going around obstacles and things like this, they were able to fire their cannons in such a way that it integrated where that trajectory is going to go relative to the projected winds at these very, very fine scales moving around terrain.
Didn't ask the artillerymen to...
No,
to
it was built into the system, so the computers did everything. The computers knew when to move operations from one place to another because of inversions, trap sound, all these things. They could work with this evolving weather situation, and built into their systems was this ability to understand the complex flows around mountains, which you could not put a person in a weather briefing up in front of a weather map to explain this. It's just so complex.
But wouldn't you say also that it's too complex for the computers in certain ways? That there are certain things we need to learn about processing that kind of information? That's a pretty hefty processing problem, isn't it?
Yes, it is hefty, and that's where a lot of the research was.
Yeah.
And some of the things are not believable. They have low probabilities. But when you're in complex terrain, interestingly enough, the flow moves around obstacles fairly predictably. Like on windy days and you work in a high-rise building, you know where the wind's going to be blowing. You hold your hat when you walk over there.
Sure.
You know all these complex flows in your own little world. But when you're firing artillery in complex terrain, there's all kinds of complex flows out there you may not be personally aware of, or how would you know where to aim that when it's going to go through a little burst there, a little wind there. You're aiming these things for several kilometers.
You may not even have the observations.
Yeah, but you can, from the basic weather setup, you can actually determine these complex flows with models, and you can build them directly into the infrastructure. just like you can do it with wind farms and air travel, airports where you can route planes. You can use all this complex information in some way if you know how to build this probabilistic information into the infrastructure.
I get the sense there's a lot of work for you in the future still.
Oh, absolutely, yeah. It's very exciting. And we're just scratching the surface of what we can do.
Yeah.
And I think, yeah, the sky's the limit in the future. There's just so many applications that we've yet to explore.
Well, I've learned a lot, Greg. I wish we had more time to talk more because there's much more to learn, but this will be an exciting week, I hope, at
Yes.
AMS.
Yeah.
Thank you again.
Thank you.